Okay, going back to our main goal. Remember that we proposed a solution to the wave equation that was a series with sign involving the sine function, and there were coefficients an and bn that we had no idea how to find them. Okay, so we mainly have two questions. How to get those solutions, because we didn't explain that yet. And the other question is, okay, once I have that expression of solution, how can I compute those coefficients? And with this background that we just saw about periodic functions, we will be able to say how to compute these coefficients an and bn. So we partially answer our main goal of today. Okay, so we observe the following facts. Given p positive, which will be in the future related to the period of a function, all these functions, the function that all the time 1, the function cosine pi over px, cosine 2 pi over px, and 3 pi over px, and same for any n natural number, and sine of pi over px, 2 pi over px, 3 pi over px, and so on and so on. All these functions are 2p periodic. You just can compute that by hand. Just look at the definition of being a 2p periodic function and you will get it. Okay, so we have all these functions 2p periodic. We have here the computation, so we can take a look. So let's start with cosine of n pi over p x pi 2p. We just distribute here these numbers to get exactly this, and now we know that cosine of y is equal to cosine of y plus 2p. And once we have a period, then we know that doing this, repeating this identity that we have here n times, we will get this identity here. So that's why we have this identity here. Okay, so that's we can do the same for sine for this the other family. Let's say that we did the proof of this family, and for this is exactly the same. Okay, so we have all these functions with 2p that are 2p periodic. And these functions are super special because they verify these orthogonality relations that if I multiply them, I pick I pick two cosines of that family with different, with n and m, two natural numbers, and you can compute this integral here, and you will get, in case they are exactly the same natural number, m and n are exactly the same, we will get a p. And when they are different, we will get a 0. Okay, so that happens when we pick two cosines with m and n. Then when we pick two sines, we have exactly the same. If m and n are the same, we get a p. If they are different, we get a 0. Okay, and last orthogonality property, if we pick one cosine and one sine, this is 0. No matter if n and m are equal or not, it's always 0. And these properties are quite nice. You will see in a moment why. And if you want to check these identities that are here and that we are not going to check them now, you can use these trigonometric identities So for the first one, you will need this expression, this simplification of this expression when we multiply two cosine functions, cosine of alpha, cosine of beta. We have this identity, and this identity will help to integrate this first integral here, and then this second trigonometric identity will help for the second orthogonality relations, and this one for the third one. Okay, where you obviously replace alpha with n pi over px and beta by pi over px. And we leave that as an exercise. You don't have to do it, but if you want to practice how to compute these integrals, you can do it. Okay, so we have all the ingredients to partially achieve our goal. We already said that. Which functions f admit a Fourier series representation of this form? And how to find the coefficients a0, a1, a2, b1, b2. So this will be a goal for the next lecture. So now we are going to focus on how to find these coefficients, and this is quite simple once we have these orthogonality conditions, orthogonality relations that we already saw. So assume f actually has this Fourier series representation. So we are assuming that f has this form. So we can write f as a constant a0, which is this constant a0. You can think about a0 times 1, and 1 was the first function of this family that we introduced at the beginning of this lecture. Remember, that was 1 cosine of pi over px, cosine of 2 pi over px, and so on and so on, and sine pi over px, sine 2 pi over px, and so on and so on. So we are kind of writing f with number times this function 1, number times the first cosine, number times plus number, other number, the second cosine, and so on and so on, and the same with the sine function. So it's a infinite combination, linear combination of that family that we introduced at the beginning of this part of the lecture. Okay, so assuming f has exactly this form, we integrate f in the interval minus p. And we are assuming, I don't know if I said it here, that this f is a 2p periodic function. Okay, maybe it's written a bit earlier, but okay, if p has this form, p is a 2p periodic function, because remember that we proved that each of these guys is a 2p periodic function, and then we are taking, and also this one here, so, and taking this infinitive linear combination would be also a 2p periodic function. Okay, so first we compute this integral of f on the interval minus pp. Okay, so we just replace f here, and we split this integral in these pieces. So we get constant and the measure of the interval, which is 2p, and then we have this integral that you can see that is equal to 0, and this integral that is equal to 0, which is also an exercise. You have to find an antiderivative of this function and then evaluate on the extremes of the interval. Okay, so what we get, since these guys are gone, is that we found exactly the expression for a0. a0 is just the integral of f from minus p to p over 2p, which is what we have here. So we find the expression for a0, the first coefficient of f. To find the coefficients an, for n equal to 1, 2, 3, and so on, we compute this integral, f times cosine of this m pi over px. So again, we have f, we put the expression of f, which is a0 plus the series of cosines plus the series of sines, and replacing that we have a0 times this cosine times another one, and cosine times sine, where this m is fixed at the beginning and n is varying here with the series. Okay, so now I think you can see why those orthogonality relations are important, because now it's quite easy to see, look, this was the first orthogonality relation, and we know that this is equal to p if m and n are equal, and 0 if they are not equal. And same here, we know that no matter if m or n are equal or not, this is exactly 0. So this guy is gone. This guy, we have p or 0 depending on n and m. And okay, again, this was part of the previous exercise that you have to check that that is 0. Okay, so what we get here is expression for am or an, no matter, yeah, let's say am is the same. Because we just put this p when it's 0, okay, we get we don't get anything. So when m is equal to n, we get this p, and the only term that survives here in the series is m, and that's why we have this identity here. Okay, so we already have a0, we already have am. a0 we obtain that one integrating only f, which is also integrating f times 1. We get this am integrating f times cosine m pi over px, and as you can imagine, we will get bm integrating f times sine m pi over px, and we will get this expression, again using the orthogonality relations that we saw before. So we already answered that if we assume f has a Fourier series representation in this way, a0 plus this series of an cosine n pi over px plus bn sine n pi over px, if we have this series representation, this Fourier series representation, then we can compute the Fourier coefficients of f, which are these a0, an, and bn, with these formulas that are called Euler's formulas. And it's just what we have before. We get a0 making this computation, and we find, we find an making this computation and bn making this computation. Okay, so each time you have to find a Fourier series representation, you don't have to deduce all these formulas. You can just apply these formulas here. Okay. We also have these alternative Euler formulas, which is changing this interval that was minus pp for this 0 to p. Since we are working with 2p periodic functions, it doesn't matter where the particular interval where we are integrating. The only thing that we have to take care is that the interval has length 2p. So before it was minus pp, that interval has length 2p, but this new interval 0 to p is also valid because it also has length 2p. So you can use whatever you want. The previous one of this with 0 to p is the same. So example, to try to fix these ideas. We have this function defining in 0 to pi. Okay, this function here, 1/2 times pi minus x, which is again quite similar to our fourth example in the second part of the lecture. So we have a 2 pi periodic function. As you can see here in the graph, we have this line, and this line repeats itself in each interval of measure of length 2 pi. Just to mention a little bit, those are the points where the function has some discontinuities, but we won't care much about that now. So imagine that we want to find the Fourier series representation of this f. That means that we need to find the Fourier coefficients of this f. So we are going to use this Euler's formula, which is okay. So the first coefficient A0, we can compute it with the formula. Now here, notice that the period is 2 pi here, and we are using here the alternative Euler's formula with 0 and 2 pi instead of minus pi. We have f here. Okay, we find an antiderivative of f here. We evaluate in the extremes of the interval, and then we get this 0 here. So we have already the first value, a0 is equal to 0. For an, we use again this Euler's formula. So it's 1 over p. So p here is equal to pi. And we have to integrate f times this cosine, depending on n. Okay, we can use integration by parts. Here it's not set, but we are using integration by parts. And then we compute this in this way. We have an antiderivative of cosine nx, and then we evaluate at the extremes, and then notice that this is equal to 0. And here we use parts again. Sorry, here we are not using integration by parts. We are just distributing this this pi here and this x here. Okay. But also, if you want to save some computation, we can also use integration by parts in this step instead of doing this distributed property. Okay, so now integration by parts, which is this formula here. We choose u equal to x, so the derivative is only 1, and we simplify the integral then in the future calculation. We choose b prime to be cosine nx, so b could be this guy, sine nx over n. And okay, we use this integration by formula. Again, notice that this has this antiderivative, and okay, this finally the final value of this piece is 0. And then we have this sine 2 pi n over n, which is also 0. So an is 0 for every n. So far a0 is equal to 0, an is equal to 0, and finally we get this bn integrating our f times sine of n pi over pi, because here pi is equal to p. Again, here I did this distributed property, but we can also use parts here to maybe simplify a bit the computation. But okay, if we don't realize, we just do integration by parts in the next step. Again, taking u equal to x, b prime equal to sine nx. So we have this new function, u prime is equal to u, and b is minus cosine x nx over n. So by integration by parts, we have this expression here. And this is equal to 0. Here you have the antiderivative of this part. So that's why this term is 0. And then you have to evaluate in the extremes on the interval, and we get 0. So then what we have here is 1 over n, and observe that cosine of 2 pi n, no matter the n, is always equal to 1. So that's why we finally get bn is equal to 1 over n for every n. So gathering all the information that we have, our f finally can be written in this way. It's the series from n equal to 1 to infinity of 1 over n sine of n times x. So this guy is the Fourier series representation of our f of x, our function f. Okay, and that's how we compute the Fourier coefficients of the Fourier series representation of a periodic function f. So we have the following question. Can we say that this Fourier series representation of f is exactly f? Okay, and here is where we have this continuity concept and discontinuity concept involved, because we will have this identity for all the points where f is continuous. And for those where f is not continuous, we have an identity but not equal to f of x. So let's talk a little bit about this question. Okay, so remember that a series is just the limit of its partial sums. Okay, so computing these partial sums for some values of n, you can see that what we get is these guys, the partial sums go to f of x, where x is strictly in the open interval 0 to pi. And this interval contains the points where f is continuous. So we can say that we have this identity, this huge identity, when the x is between 0 and 2 pi, strictly speaking. But when we are in these points of these continuities, minus 6 pi, minus 4 pi, minus 2 pi, 0, 2 pi, and so on, in all these points, which we can write plus or minus 2 pi k with k in n. If we take a look at the partial sums in these points where f is discontinuous, so these are the partial sums in these points. So we just replace x by these points, and we have sine of 2 pi plus or minus 2 pi n times k, and whatever is the value of n and whatever is the value of k, this is always 0, okay? And f in these points, so we are here, right? Okay, so we have the partial sums in these complicated points, let's say in these points of discontinuity of f, the partial sum is 0, and then of course the final limit and the complete series is 0 in these special points. And remember that our function in the points of discontinuity doesn't take the value 0. We can check now, but it was something like -1 and 1 in the, but maybe with the constant. Here we have the value, sorry. So observe that f in these points is not 0, it's -π/2. So we cannot claim that the Fourier series representation is equal to f in every point. We can for sure say that the Fourier series representation of f is equal to f at x for all the x where f is continuous. But when f is not continuous, we cannot say we have this identity, which is written exactly here. The Fourier series representation is not equal to f in these points. But there is a good news, because this 0 comes from the following. It's the average between the right and the left limit in these points. Oops. Okay, so we are here again. Sorry for this, moving the screen so much. Okay, so the points, this 0 that we have as the limit of this Fourier series representation is not f, but is quite related to f. It's the average of these right and left limits. Okay, and what is happening in this example happens in general. Each time we have a periodic function and its series representation, we will have that the Fourier series representation is equal to f at points of continuity of x and equal to this average of right and left limit of the point when f is discontinuous at that point. Okay, so here is the conclusion for the example. We can say that the Fourier series representation is exactly f of x for all points where f is continuous, and is not f, but is nice because it's the average of these left and right limits at x, where the x is a discontinuity point of f. Okay, so in general, if f is a 2p periodic function, piecewise smooth function, then we have this. The Fourier series representation of f is exactly the average of the right and left limits of f at x, where this guy a0, am, bn are given by this Euler's formula. And just a final remark that if f is continuous at x, then this average is exactly f at x. And we have then that the Fourier series representation is exactly f at x, coincides with f at x. Okay, so that finished the lecture of today, where we already answered how to find, given a function that has a Fourier series representation, how to say this with these Euler formulas. And then we see how to compute them from this example, for instance. And now you can read these sections of the book, but well, okay, you don't have to pay attention now about this because it will be in on Blackboard too. These are the sections that we were talking about today and the exercise that we will work on in the section exercise this week. Okay, so that's it.